Hello class, welcome back. We're going to continue with signal transduction. This is going to be part 12. And we were talking about when we stopped last, we were talking about the sympathetic nerve ending. Talking about a sympathetic nerve ending. So let's just bring that back up. And let's do a little review. To make a sympathetic nerve, to make norepinephrine, which comes out of sympathetic nerve endings. And here we have the structure of norepinephrine. But we start with tyrosine. Tyrosine comes through a tyrosine transporter. It's hydroxylated by tyrosine hydroxylase to make dopa. And that's when you make a catechol, when you add this 3-hydroxyl. Dopa is then decarboxylated by dopa decarboxylase to make dopamine. And so we remove the carboxyl group, the alpha carboxyl group. The dopamine goes into a vesicle through this transporter, and then the dopamine is acted on by dopamine beta hydroxylase, and it adds this hydroxyl group on this beta carbon to make norepinephrine. Now the norepinephrine. Next thing that happens, this vesicle, this entire vesicle, goes over and it fuses with the membrane. Let's see if I can make this work. There we are. It fuses with the membrane. And when it fuses with the membrane, the norepinephrine leaves the vesicle and it goes and it binds to the beta 1. If we're just going to say here that the effector organ is the heart. It binds to the beta 1 adrenergic receptor on the heart. And what happens to the heart when norepinephrine binds to the beta 1 adrenergic receptors? Contraction increases. There's greater strength of the contraction. Now, do you want this norepinephrine to stay there all of the time? No. So we need to come up with ways to get rid of it. One way that I'm going to put this back for now. We're just going to work with this norepinephrine. One way that we can get rid of the norepinephrine that's in this cleft is to degrade it with an enzyme. Catechol O-methyltransferase destroys some of the norepinephrine. Now, before I start getting into the regulation and the drugs here, just be aware. Now, I did put here a beta 1 adrenergic receptor, but you can have any adrenergic receptor. Let's say we're in the let's say, for example, we're in the smooth muscle in the blood vessels leading to your skeletal muscle. Then you'll still have an adrenergic receptor here, but here it's going to be beta 2. So we can have beta 2 here also. Or if it's in smooth muscles leading in the blood vessels going to the stomach or to the gastrointestinal tract, then you'll have alpha 1s. So that the effector organs can have, depending on what effector organ you're talking about, the adrenergic receptors will be different. Does that part make sense? Additionally, any of these can be in the central nervous system. For example, things like neurotransmitters like norepinephrine and serotonin in your central nervous system, when they bind to the receptors, neurotransmitters make you feel happy. Even though it sounds almost oxymoronic, you would think if norepinephrine is produced during stressful situations, that means secreting a sympathetic or secreting norepinephrine should make you feel bad because that's stressful. But you want to think about it like this. If it's a parasympathetic response, you're really relaxed and lackadaisical. But the sympathetic response, like norepinephrine, those things, even if the situation is stressful, they pimp you up. So one of them, parasympathetic, almost makes you sad and makes you down and low. Sympathetic neurotransmitters lift you up. They make you happy, and they give you a sense of good feeling. Okay, just try to remember that. That's kind of important. So, if you're in your central nervous system, if you get a neurotransmitter produced, like norepinephrine, especially an adrenergic neurotransmitter, you're going to feel happier. Okay, and so because these are used a lot in psychological situations. Now, a question for you. Let's see if you understand this. Now, let's say here we have norepinephrine in this space here. It was bound to one of these receptors. Now it's done its job, and we need to get rid of it. And so we're going to use catechol O-methyltransferase to get rid of this neurotransmitter. Now, if this person were treated with a COMT inhibitor, now this is a question. If this individual is treated with a COMT inhibitor, would this person feel happier or would this person feel sad? I want you to think about it for 3 seconds. Question again. If this person were treated with a COMT inhibitor, and COMT, catechol O-methyltransferase, destroys the neurotransmitter norepinephrine, would this person feel happier or would this person feel sadder? Does everyone understand the question first? Okay. 1, 2, 3. Okay. Who think they have the answer? Okay. What do you say? This person would be happier, and that is exactly the case, because you're going to have more. There are going to be more of the neurotransmitters still left to continue to bind to the receptor. Does that make sense? Okay, very good, very good. Now, let's look at something else here. Now, that's one way to destroy the norepinephrine. Another way to get that norepinephrine out of the cleft here is this norepinephrine will go down and it'll go through this reuptake channel. It'll go through this reuptake channel and it'll come back into the cell. It's going to come, so this norepinephrine can come back into the cell through this reuptake channel. And we call this reuptake 1. And so I'm going to go ahead and give it a name because I'm going to be talking about it. Okay. And so this substance here is called reuptake 1. This channel. I'm going to make it green so we'll know what I'm talking about. It's called reuptake RU1. Reuptake 1. Now, when the norepinephrine gets back into the cell, it tries its best. The norepinephrine is going to try here. So this is the norepinephrine. As soon as it gets back into the cell, there's an enzyme that wants to destroy it. Monoamine oxidase wants to destroy the epinephrine. So the norepinephrine. So the norepinephrine tries to run around here really fast and go back through this channel here and get back into the vesicle. But if it doesn't make it fast enough, if it does not get into that vesicle fast enough, this monoamine oxidase is going to destroy it. Does that part make sense to everyone? Okay, let's go back. Let's make sure everybody understands this, because you have to understand what's going on, or the drugs won't make sense. Why people take certain drugs. Okay, what's going to happen? The norepinephrine is in the vesicle. Let's say it was bound. It releases. Now the norepinephrine comes back into the cell through reuptake 1. It reuptakes the neurotransmitter. Now, the neurotransmitter tries its best to get into this vesicle, back into this vesicle as fast as it can. If it doesn't get into the vesicle fast enough, this enzyme, monoamine oxidase, is going to destroy the norepinephrine. Does everyone understand that? Because I'm going to have 2 questions for you now. The first question is this. Reuptake 1. If we have an individual and we give them a reuptake 1 inhibitor, is this person going to be happier or is this person going to be sadder? Again, the question. If you give a person a reuptake 1 inhibitor so that the norepinephrine can't get back into the cell, is this person going to be a happier person or is this person going to be a sadder person? Okay? Okay. Oh, y'all already gave me the answer. What was the answer going to be? Okay, sad. And I was going to try to give you like some sort of qualifier before this, but in actuality, this person is going to be happier. It's going to be happier. Because you can almost think about it in two ways. You can think about, well, if you get, let's go with the sadder, you all said. If it gets back into the cell, if you get a lot of it back into the cell, then it's going to go and come back in here, and you're going to have more of the norepinephrine here. That's one way to think about it. Or you can think about it this way: if there's no if the reuptake 1 is inhibited, then the norepinephrine can't get back into the cell. Now it's going to stay in the cleft, and now it's going to continue to activate the adrenergic receptor, and that's going to make the person happier. And that's actually what happens. It makes the person feel happier. Okay. Some of your antidepressants work at this reuptake 1 inhibitor, and there are some. I'm gonna mention a few of them. Let's see which one I want you to know. I'm gonna give you like 4 antidepressants that I want you to know that inhibit reuptake 1. Okay, and so I'm gonna put them like up here. I'm going to put it on this slide. We're here with reuptake 1. What if I put it right here, right in this small space right here? Yes. And I'll just make it really small. These are going to be our reuptake 1 inhibitors. The first one is going to be desipramine. D-E-S-I-P-R-A-M-I-N-E. Desipramine. So if a person takes desipramine, it's going to make them happier. The next one is going to be a group of antidepressants called your tricyclic antidepressants, or your TADs, your tricyclic antidepressants. And we know how they work now. They block reuptake 1, keep more norepinephrine in the cleft there, and so there's more of an adrenergic response. Make sense? The next one is going to be serotonin-specific reuptake inhibitors. And so these inhibit. And so there's a reuptake transporter for serotonin, and serotonin makes you happy. And so like lots of people like things like ice cream. They eat ice cream because ice cream really has fats in it, and those fats release serotonin. And so eating ice cream actually makes you feel happy. And people like animals like sex because that releases serotonin, and that makes you feel happy. And the last one is going to be not a drug I would like for you all to take, but it is a drug. It makes you feel happy. Cocaine. Cocaine blocks reuptake 1. That's one of its mechanisms. And it makes you feel happy. That's why a lot of people take it. Kind of makes sense? Excellent. So you all did okay on that one. So you got the answer right for the COMT inhibitor, but you missed the one for the reuptake 1 inhibitor. But now it should make sense. Correct? Excellent. Now let's go back over here. Let's go here now. Let's go to the monoamine oxidase. Monoamine oxidase. And so what's going to happen here, if this norepinephrine can't get back into this vesicle fast enough, then monoamine oxidase is going to destroy it. It's going to destroy it. So now, this is the question. If you give someone a monoamine oxidase inhibitor, if you give someone a monoamine oxidase inhibitor, is that person going to feel happier, or is that person going to feel sadder? Okay. If you give a person a monoamine oxidase inhibitor to block the monoamine, is that person going to be happier, or is that person going to be sadder? What is the answer? Okay, I got a happier there. 2 people say happier. What do the rest of you say? Some people, who said sad? So some people say sad, sad, sad. Okay. The answer is actually happier. You're going to feel happier because if you don't break the norepinephrine down, then you're going to have more to put in the vesicle. And so the next response, you're going to have even more norepinephrine. Does that make sense? Okay. And so there's one, let me see. Is there a monoamine oxidase inhibitor? Well, I'll give you one monoamine oxidase inhibitor. No, I'm not. Just know what monoamine oxidase inhibitors do. Question. If it blocks the monoamine oxidase, see what the monoamine oxidase does, it takes the norepinephrine and it destroys it. So if you have a monoamine oxidase inhibitor to block that enzyme, you don't destroy the norepinephrine. So you're going to have even more norepinephrine to go back into the vesicles, and now the next action potential, you're going to release even more norepinephrine, and you're going to have even more epinephrine binding to those central nervous system receptors. And you're going to make you feel happy. It's going to make you feel happier. It's going to take you out of your depression. So monoamine oxidase inhibitors are antidepressants. Make sense? Excellent. Excellent. Let's see if you'll get this one. So some of you got that one right. Some of you missed that one. So make sure you understand this. Now, there is a channel that lets the norepinephrine get back into the vesicle, that allows the norepinephrine to get back into the vesicle. Okay, now, here's the question. Let's say you have an inhibitor. Okay, and you have an inhibitor here, and that inhibitor actually, let's see, where's the vesicle? We'll put it here. This inhibitor actually blocks this vesicle. It blocks this transporter here. So now, the norepinephrine, even though it wants to get back into that vesicle, the norepinephrine can't get back into the vesicle. It can't get back in. Now the question is, if you have an inhibitor that blocks that transporter going back into that vesicle, is this person going to feel happier, or is this person going to feel sadder? Okay, I have two sads. Anyone else? Sad. Shaw? Happier? Okay. Now, what actually is going to happen, this person, now if norepinephrine is going to try to go in, it can't go in, and so it's going to be destroyed by monoamine oxidase. You're going to have less norepinephrine. Now when the vesicle fuses, there's going to be less norepinephrine, and that person is going to feel sad. The person is going to feel sad. Does that make sense? Okay. I need you to know the name of this inhibitor here. This inhibitor is called reserpine. It is an antidepressant. No. Reserpine is going to make you, it's going to be like a downer. It's going to make you go, no, it's not going to be an antidepressant. It's going to be a depressant. It's going to make you feel sad. Reserpine. Because it's going to make you feel sad. So two drugs work here. Reserpine. Yep, reserpine, that'll be the good one. Let's see, we have some more. Let's do a... that was not on here. Okay, yes, here it is. Okay, now reserpine is a sedative. It's a sedative. It makes you sleepy. And that should make sense. Right? Now, has anyone ever heard of the drug Prozac? What does Prozac do? What kind of drug is it? It's an upper. Or what is another word for an upper? Or a stimulant? Or an antidepressant. So Prozac is an antidepressant. So it can work in, let's see, where do antidepressants work? Okay? They could do Prozac. Let's see if you all could just figure out where Prozac is going to work. Do you think it inhibits COMT? Does it inhibit reuptake 1? or does it inhibit the MAO? I mean, there's no way to know the answer but I'm going to tell you in just a second. But let's see if anyone can just figure it out. What do you think it inhibits? COMT, RU1, or MAO? COMT. Okay, I got two answers, and both of those were the wrong ones. There was only one left. It inhibits RU1. RU1. So we're going to put here, Prozac is another one that works here. So a lot of them work at that RU1. Prozac. And so there are lots of drugs here. Okay. So everyone okay with those? Trying to see if there's any more I need you to know about. Anything else I need you to know about this? Okay. There's one final thing I need you to know about the nerve ending itself. Okay. So I'm going to actually get rid of this norepinephrine here for just a second. Now, when the norepinephrine comes out of the vesicle, it can bind to the receptors on the effector organ. However, if there's norepinephrine already in this area here, you don't need for the nerve ending to continue to make more norepinephrine because there's already some there. Does that rationale make sense before I explain what's going to happen? Again, I'm going to repeat this. Once the norepinephrine comes out of the vesicle, and there's a lot of norepinephrine in here, you don't need for this nerve ending to continue to synthesize more norepinephrine and release more epinephrine because there's already enough made. Does that make sense? So what you need for this nerve ending to do, you need to be this nerve ending to sense norepinephrine and turn the inside of that vesicle off. And so we need to put some sort of receptor on here that will turn this nerve ending off. Everybody understand where we're trying to go? Now what I'm going to do, I'm going to actually put the receptor here. That's going to lead to the turning off of this nerve ending. Okay, let's put ourselves a receptor. Select a good color here. Let's put our receptor. There's a receptor. And so now we have a receptor. So what's going to happen? When this norepinephrine binds to this receptor, you're going to turn off this nerve ending and stop it from metabolizing more norepinephrine, from creating synthesizing more norepinephrine, or releasing more norepinephrine. Makes sense where we're going. That's where we're ready to go. Now we need to come up with a name for this receptor that actually... So is this receptor here, is this receptor going to inhibit the nerve ending, or is it going to stimulate the nerve ending? It's going to inhibit the nerve ending. So you all should know what receptor this is going to be. What receptor is this going to be if it's going to inhibit this cell? It is a presynaptic nerve ending. Not beta 2, not cholinergic. Alpha 2. Alpha 2, remember those exceptions. Alpha 2 is one of those exceptions. So this is going to be an alpha 2 adrenergic receptor. And so now this alpha 2 adrenergic receptor is going to be connected to what inside? Which G protein? G inhibitory. Exactly. And G inhibitory is going to inhibit what enzyme? Adenylyl cyclase. And if adenylyl cyclase is inhibited, that's going to lower the production of what metabolite? What metabolite is not going to be created? Cyclic AMP. And if cyclic AMP is not produced, what protein is inhibited? Protein kinase A is inhibited. And if protein kinase A is inhibited, what's not going to come into the cell? Exactly, cations, like calcium. And so is this going to turn this, if calcium doesn't come into this cell, is this cell going to be on or off? It's going to be off. And so when this cell is turned off, you don't get the production of, you don't get any norepinephrine produced, and you don't get any vesicles fusing with the membrane, and you don't release more norepinephrine. Make sense? And now we know how all of our receptors work. We have to know how all of our adrenergic receptors work. So we're going to say we're through with the biochemistry of our adrenergic receptors. Now what we're going to do, I didn't want to put this on a well, yes I do. I want to do this by itself because we've talked about how tyrosine goes to make norepinephrine, but we're gonna actually we're gonna look at this more formally now. Okay. Any questions about nerve endings, adrenergic nerve endings? Okay. Excellent. Excellent. Let us continue. Okay. Let's look at the synthesis of norepinephrine from what amino acid? Tyrosine. Okay. So I'm going to put it right here. So I'm going to draw the amino acid tyrosine. So here we have the amino group, the alpha carbon, the carboxylic acid group, phenylalanine, okay. So this is the amino acid tyrosine. That's our amino acid tyrosine. You all should be familiar with that one. Now, the first thing that has to happen to convert tyrosine into norepinephrine is we have to make a catechol. This is not a catechol. This is just a phenol because it only has one H. It only has one hydroxyl group. Or it's a parahydroxyl group. Orthometapara, or really a 4-hydroxyl. Or you can call it a 4-hydroxyl. And so this is a 4-hydroxyl. And so we need to put another hydroxyl group. I could just copy it. Yeah, I could just copy this and move it over, but then you all would have to draw it over again. So I'm not going to copy it. I'm not going to do that. I'm going to actually just draw it over because you all will have to do it too. So what I'm going to do now is we have to add a hydroxyl group here. A 3-hydroxyl group. So I'm going to just indicate that here. We need to add a hydroxyl group right here. And so I'm just going to put NH3 CH COOH CH2 OH and our new OH. In this compound, when you add the hydroxyl group, this compound, or the enzyme that does this, is tyrosine hydroxylase. And I'm not going to put the whole name of it. Tyrosine hydroxylase. And so what's the name of this new compound? Dopa. That compound is dopa. The old one was tyrosine, but now we formed dopa. Make sense so far? The next thing that's going to happen is we need to remove this hydroxyl group here. This hydroxyl group needs to go away. And so what I'm going to do here is redraw this without that hydroxyl group. So we're going to have NH3 alpha carbon, the H, COO. Oops. What am I doing wrong here? We don't want the hydroxyl group. CH2. All of this is the same. OH, OH, and H. And so we've taken dopa and we've removed a carboxyl group from dopa. And the enzyme that does this, what would be a good name for this enzyme that removes a carboxyl group? Exactly, dopa decarboxylase. Dopa decarboxylase removes the hydroxyl group. And this new compound, what should we call this new compound? Dopamine. And now we only have one more step to go. It's a real simple synthesis. Now the next thing we have to do is one of these H's here. Let's see which one that is. Okay, this is the one I want. Where is it? Oh, there it is. We're going to replace. I hate to do this to you all, but I want these H's beside each other, drawn explicitly. So we're going to have two H's here, and what we're going to do, we're going to hydroxylate this carbon here. So we're going to remove one of these H's and add an hydroxyl group, a beta, because this is the alpha carbon. That's alpha. This is beta. So we're going to beta hydroxylate this compound here. So we're going to have NH3 CH H CH2. Oh, before we continue, this alpha carbon here, is it chiral or achiral? It's achiral. Why? Because you have two hydrogens, exactly. So what we're going to do now, you're going to have just one H, and we'll hydroxylate it later. Now we're going to have OH here. We're going to have an OH here on this beta carbon, and we've already replaced this one. So now what we've done, we have actually hydroxylated dopamine at the beta carbon. And so we can come up with a really good name for this compound, the enzyme that does this. What would be a good name for the enzyme that adds a hydroxyl group at the beta carbon of dopamine? Dopamine beta hydroxylase. And what's the name of this compound that we formed? This beautiful compound? Norepinephrine. Exactly. Norepinephrine. Okay, everybody okay with that? Excellent, excellent. The last thing, so we have our neurotransmitter. We know where our receptors are. What makes the receptors different? Why is one adrenergic receptor different from another adrenergic receptor? Let's explore. Let me see if I hope I have my notes for that, because I can remember. Well, we'll just introduce it, because it's hard to remember those. Okay, how are we going to do this? Okay. Now, the receptors, I'm going to draw here a typical 1, 2, 3, 4, 5, 6, 7. Okay, this is how we've been drawing our adrenergic receptors, correct? Now, if you will allow me, for this explanation, let's only focus on this part of the adrenergic receptor. Let's only focus on that part of the adrenergic receptor. And so, first thing I'm going to do is draw epinephrine. I'm going to draw epinephrine. So, I'm going to draw it on its side. Okay. And let's see if this makes sense. Well, that's okay. What I'm going to do, I'm going to draw epinephrine just like this. And hopefully this will make sense. I'm going to put an OH here, and I'm going to put an OH here. Then I'm going to add my here, and put my amino group. Then I'm going to put my amino group. Well, this will be norepinephrine. Just want to make sure I get that structure right first. Okay? Right, exactly. My beta, because this is alpha, beta. So we have to have a beta hydroxylation. Okay? And that's norepinephrine. Everybody okay with that one? Now, oh, right. What am I making? What kind of compound is this? Yes, excellent. Now we have norepinephrine. Everybody okay with it now? Now, but we actually want to work with epinephrine first. So, how do I turn, what is the difference between this compound, norepinephrine, and epinephrine? There's one change. So all you have to do to make epinephrine is, on this amino group, take away one of the H's and put a methyl group. So I'm gonna get rid of one of these H's here, and I'm gonna put a methyl group, CH3. This is now epinephrine. Not norepinephrine, it's epinephrine. So epinephrine is basically methylated norepinephrine. Now this is the reasoning. This is what I want you all to think about. Think about it like this. So which one of them is bigger? I'm going to actually erase this and do something. I'm going to actually put my CH3s. Okay. Here we have the left side. We'll say this is the left side, and this is the right side. Or we can call it the catechol end and the amino end. Okay. On the catechol end, which one has the bigger functional group? Norepinephrine or epinephrine? On the catechol end, which has the largest functional group? Exactly, they're the same. I was going to trick someone there. Everyone see that? Now, on the amino end, which one of them has the larger functional group? Norepinephrine or epinephrine? Okay, I got different answers. I'm going to repeat the question. On the amino end, which has the larger functional group? Norepinephrine or epinephrine? Epinephrine, because epinephrine has that big methyl group, whereas norepinephrine only has a hydrogen. Okay. This is what I want you to be thinking about before we meet next. If you have, I gotta get my order right. If you have this is going to be where our catechol ring binds, and this is going to be where my amino group end binds. This receptor here that can bind, that has a medium-sized amino binding region, a receptor like this is going to be like a beta 2 receptor. Beta 2. It's going to have the size of this is kind of medium sized. No, that's really beta 1. I would say that's beta 1. Yeah, beta 1. But now, if you make that amino end really big, that can bind something even bigger, that's beta 2. And if the amino end can bind something that's really small, that's going to be alpha 1. And if the amino end can bind something that's bigger than alpha 1 but smaller than beta 1, we're going to call that alpha 2. And so the different receptors, differ by how large the amino end of the compound is. If it gets bigger and bigger, you start bothering beta 2s. If you get smaller and smaller, you get down to alpha 1. And that's what we're going to talk about when we meet next time. We're going to talk about what those different compounds are that bind these different receptors specifically. Kind of makes sense? No questions for you all today? Have a great day, you all.